Good afternoon, everybody. Welcome to lecture. So today we're going to continue our discussion of NMR spectroscopy. We're going to do some sample problems. We're going to try to do some spectra interpretation, kind of like we ended with at the last lecture, to get some practice looking at an NMR spectrum and pulling out all the information you can from it. Remember, there's four kinds of information you can get out of a proton NMR spectrum. There's the number of signals. How many signals you see gives you the number of unique proton types. Then there's the chemical shifts of those signals, which tells you the chemical environment of those protons. Then there's integration values, which tells you how many they're representing, the ratio. And then there's spin-spin splitting, which can tell you what kinds of neighbors are nearby, what is next door to that clump of protons, proton or clump of protons. So we're going to do that. But first, we're going to do a survey question. This is an NMR-based survey question. It has to do with applying the N+1 rule. And really, it's about counting number of neighbors. So these are surprisingly challenging, I have found, on exams and homeworks and things. It might seem simple, but let's look at this one and try to decide what the right answer is. So this asks, how many peaks would the signal for the proton indicated by the arrow be split into in the proton NMR spectrum of this molecule? So there's a proton that's being indicated here. And then the thing is, you just need to count the number of neighbor protons. So these are the number of protons that are within 3 bonds to act as neighbors. And sometimes the H's are drawn out. Like in this case, if you count and look next door on a next door carbon, there's 1, 2, 3 bonds between that H and that H. So that's definitely a neighbor. There's also 3 bonds between the H here indicated by the arrow and that H. So these two definitely count as neighbors. If you try to go further, though, these H's, it's 1, 2, 3, 4 bonds between these H's, that CH2, and these. So these don't count as neighbors. It's only very rarely that you see the 4-bond coupling, and we haven't seen any examples in this course. So these wouldn't count as neighbors. So these are our 2 neighbors. Now, the thing you have to be careful of, though, is that you don't forget to count something and it doesn't look like, there's no bonds indicated here, these H's and the C, it's just labeled as CH3, but these H's and those H's, these protons that are in this condensed part of the structure, they are within 3 bonds also, because you've got 1 bond here, 2 bonds here, and then the 3rd bond is the bond between the carbon and each of the hydrogens. So these are neighbors and those are neighbors. Yeah, I got to add them all up. So there's 3 here, 3 there, that's 6, plus 2 more is 8. So there's 8 neighbors, add 1, you get 9. So the answer is no net. A no net is actually kind of common because this type of functional group is, or this type of arrangement of atoms, this type of alkyl group is pretty common. And it's hard to distinguish a no net from a septet because when you get to these really highly split multiplets, the outer peaks become so small that it's difficult to see them. But they are actually there. If you look closely enough, you'll be able to see them. So a no net is the one you would expect for that one. So this just happens to be a molecule that's present in bananas that gives them their characteristic odor and flavor. So it's one that makes bananas smell and taste distinctly like bananas. So let's take a look at the class statistics on this one and see how people did. All right, survey statistics kind of all over the place in terms of what answers people selected. E was the most popular answer. That's good. That was the correct answer. But there's a significant number of people that selected the other answers. So if you were one of those people that selected a not correct answer, go back and just make sure you're counting your neighbors correctly, because it's going to be really important that when you see a proton in a molecule, you can predict how many neighbors it's going to have, or you'll have a lot of trouble interpreting spectra. So definitely work on this if this is an issue. So good. Hopefully we do this question again, like you'd get a better score, or the class would get a better score on it. That's what I'm hoping. Anyway. All right. Well, now let's go ahead and do some practice spectra, some NMR that we can try to interpret. Here's an NMR spectrum, a proton NMR spectrum, and it's asking us to figure out what this molecule is. So let's look at what we've got for data here. We're given some interesting, useful information. We're given a formula here. That is going to be really powerful stuff. So anytime you're given a formula, I recommend using the degrees of unsaturation equation to figure out how many degrees of unsaturation does the molecule have. A degree of unsaturation, just as a reminder, is a ring or a pi bond. So knowing that gives you some ideas of what structural features you should be looking for. So let's do that equation. And the way the equation works is degrees of unsaturation is equal to 2 times the number of carbons minus the number of hydrogens minus the number of halogens, if you have any, plus the number of nitrogens, if there are any, plus 2, all divided by 2. And I'll give you that equation on an exam. You won't have to memorize that. You just have to be able to use it. So when we plug this in, we're getting 2 times the number of carbons is 2 times 9, minus the number of hydrogens, 13. We don't have any halogens, so we're going to not take anything away there, but we do have a nitrogen, so there's 1 nitrogen plus 2. And for the equation, you ignore oxygens and sulfurs. So we have an oxygen in the molecule, but we don't need to worry about it because it doesn't affect the degree of unsaturation calculation. So let's look at this and do the math. So we have 2 times 9 is 18, minus 13 is 5, plus 1 is 6, plus 2 is 8, divided by 2 is 4. So degrees of unsaturation here are equal to 4. So that means there's 4 things in this molecule that give a degree of unsaturation. Could be any combination of pi bonds and rings. One of the tips I'll give you, though, is that if you have an aromatic ring in your molecule, it gives 4 degrees of unsaturation, and that's a real common structural feature. So when you look at this proton NMR spectrum, there's a couple of indications that we have from the spectra we're given that we have an aromatic ring. The first one is going to be that we have protons in the 7 part per million region. This signal right down here, 4 parts or 4 H's, those are likely to be aromatic ring H's, protons that are on an aromatic ring. The other thing that we have is we have some IR data. So we've got some other data. Let's take a look at this IR data and see what it's telling us. It's giving us that in the IR, there's what it's calling a doublet, and it's giving 3360, 3280 as frequencies. This would be easier to decipher if you had the spectrum. You'd see a broad spiked signal, and the 2 spikes would occur at the 3360 and the 3280. The way to read that is this is an H-containing molecule, and the fact that there's 2 spikes says that there's actually 2 NHs. So this is really useful stuff. We've got right now one of the pieces that we know we need to look for. We have an NH2, and of course that's attached to something, but we just don't know what yet. That's one of our pieces from the IR spectrum. The other thing that we're getting is that this is telling us that we have a 1611. And 1611 is characteristic of the C double bond Cs of an aromatic ring. So we're not given a lot of other information. We're not given information on a 1500. That's another peak that we might associate with aromatic ring, but it's just not visible in this spectrum, or they're not telling us about it. So we're pretty sure from all of this that we also have as a piece an aromatic ring. So I'll put that here. We don't know yet what it's attached to, but there it is. So a couple of pieces from the IR spectrum. The things that this IR spectrum aren't telling us is it's not telling us anything about the CHs in the molecule. That's something that if we had the actual spectrum we could look at. It's not reasonable to think that there's no CHs because there's always CHs in an organic molecule. We're just not given any information about them. So this is an IR spectrum that's got some limited information. The really big peaks that they considered important, they're telling us about, but we just don't know about the CHs. You're likely to see, if you had the spectrum in front of you, sp2 hybridized CHs from the aromatic ring, and also sp3 hybridized CHs from alkyl groups that are also present in the molecule. We're just not seeing them right now, so we'll have to worry about those later. The molecular formula is really huge, though. That information is going to be super helpful in helping us solve this structure. And then after that, we got to look at the proton NMR spectrum and get all the other information that we need out of it. Thankfully, proton NMR is really information dense, so it's going to provide us with lots of useful information. We've got the aromatic ring signal there at 7, which we're expecting based on information from the IR spectrum. And we're given an integration of 4. That's 4 hydrogens. So this is an aromatic ring that has 2 things attached to it. If it had 5 protons, if it had an integration of 5H, we'd expect 1 thing to be attached other than the 5H's. But we got 4 H's, so it's 2 things attached. One piece that you might think about based on this is aromatic ring with 2 things attached. Something on one side of the ring and something on the other side of the ring. Again, these squiggles that I'm drawing are meant to indicate that that's an attachment point to something that we don't know what's there yet, but we know there's got to be something there. And then here are the 4 H's. One there, one here, and one here. And maybe I'll just move this down here a little bit to make it a little bit more obvious. And then the signals, I'll label the signals here A and B. And as long as the two groups that are attached to the aromatic ring are different, this is what we're going to see. We're going to see a pair of what looks like doublets here, A and B signals for those H's. This is characteristic of a aromatic ring that has two things attached. They're opposite each other on the aromatic ring. So it has two unique types of protons, and they appear to look sort of like doublets. They're not actually doublets, but they appear to be doublets. So that's a big important piece. We knew we were looking for an aromatic ring. Now from the NMR spectrum, we know we're looking for a dye-substituted aromatic ring. We know we have an NH2 in this molecule. The NH2 has got to be right here because that's a singlet. And remember, NH protons don't split their neighbors, and they're not split by their neighbors. They don't participate in splitting. So our broad singlet up here, if I label these sequentially with little letters A, B, C, D, E, and the broad singlet at 1 part per million is F. The F signal is going to be the NH2. There's no other singlet that has the right area to be an NH2. There's a singlet at about 3.8, but that's got 3 H's, so it can't be that. So let's take a look at this 3H signal then at about 3.8. That's pretty far downfield. It's a singlet and it's quite de-shielded. Being 3 H's suggests it's a CH3. So I'm going to put that down, CH3. And if you think about what could it be attached to that would make it go that far downfield, that would have that big a chemical shift, it's got to be something pretty powerfully de-shielding. Being attached to the aromatic ring wouldn't be enough. If it was just attached to aromatic ring, it'd be like 2.5, maybe 2.1 to 2.5. But if it were attached to an oxygen, that would make it appear where it does, which is like in the high 3 area. And if you look at the molecular formula here, we do have an oxygen that's listed. So this is probably that oxygen in the formula, and it's attached to OCH3. All right, then the last things we have to get are, we have to get this pair of triplets here. So there's a blow up of them. So you can see they're actually triplets. They appear on the main spectrum down here between about 2.6 and 3 parts per million. And there's 2 of them. And they have integration of 2. Each has an integration of 2. And this is a pattern that you've seen before in the lab as you worked through the unknowns in the recent experiment that we did. There was an unknown in there. It was unknown H. The very last one we did was a molecule that had this kind of pattern. And this is just another example of that. The D and the E signals are from a pair of adjacent CH2 groups. So CH2, and they're attached to something, but we just don't know what yet. So one of them would be D and one of them would be E. When you do this, you've got all the pieces that you need to put the molecule together. And this is a strategy that I'd recommend, is like when you look at an NMR spectrum and when you look at IR and mass spec, it's a series of building pieces. And then once you have all the pieces, once you've interpreted all the parts of the molecule that you're being told about from the spectra, then you have to put it together into a molecule that makes sense. So that'll be the next step. We know now that we have all of the pieces that we need from the interpretation that we've done. So we've got the following things. We have a benzene ring that has 2 things on it, so that makes 2 bonds. We have an OCH3 that's going to have to go on one of the ends of the molecule. We have 2 CH2 groups that are attached to 2 things, and then we have an NH2 that has to go on the on one end of the molecule. So in order to make this work, we're going to have for sure this part of the molecule put together. We're going to have the benzene ring attached to the 2 CH2s. And then it's just a matter of what do we put where? Do we put the NH2 group on the right side adjacent to the CH2, or do we put the OCH3 group over here? And what it's going to boil down to, the best answer is going to depend on, well, what's the chemical shift of that CH2? If you put an oxygen right here, that's going to make the CH2 chemical shift be really high, like probably 4, maybe even higher than 4. And when we look at our pair of triplets, they're not that high. They're below 3. So in order for this to have the exact right chemical shifts, the NH2 has to go here. NH2 has an effect on the protons that it's next to. It deshields them, but nitrogen isn't as electronegative as oxygen, so it doesn't deshield as much. So this is the best arrangement. And then the OCH3 would go on the other side. I'm going to label the methyl peak here as C, and then our CH2's got one CH2 that's more deshielded, and then one CH2 that's less deshielded. And between the two deshielding effects, one of them is attached to the aromatic ring, and one of them is attached to the NH2. The NH2 has the bigger effect. So this CH2 over here is the one that's more deshielded. Nitrogen deshields to about 3 parts per million, whereas being attached to an aromatic ring is more like 2.5 at most. So the best assignment for chemical shift here would be to give the D signal to that CH2 and the E signal to that one. The two H's on the nitrogen are going to be labeled over here. So the nitrogen gets the F signal. And then the aromatic ring protons, I'll put those on and we'll talk about these. Getting these correct is a little trickier, and this isn't something at this stage of the course that I would expect people to get. But it turns out that there's a phenomenon that happens where if you've got a lone pair on a group, like this oxygen has a lone pair, there is a resonance effect. It pushes electron density in. It makes the positions next to it very electron rich. So they end up being more shielded than the others. And this is kind of an advanced concept that we'll deal with in a couple of chapters further down the road. So I'm not going to expect people to get this, but I'll just say that for now that the one that's the most shielded is the B signal. It's this one, the one that's near the oxygen. And then the A signal, the one that's more deshielded, is the other one. So that's the structure of the molecule. Based on all the spectra, you can put it together and that's it. This is a pretty complicated one, but if you've got time and you've got lots of information like we do, you can get it. Just one more thing I want to point out, this little blip down here, that's tetramethylsilane. That's the standard that was put into the tube to mark the 0 point on the part per million scale. So it's not anything that's in the molecule. One other thing that you might notice about this that's kind of curious is it's giving us some information up here. It's giving us some J values. It's saying J is equal to 8.7, 8.7. J here, 6.9, J 6.9. J value is something we haven't talked about. It's called a coupling constant. It's simply the distance between the peaks in the multiplet. How much space is there between the peaks in the signal, the split signal. And the reason that's useful is that if you look at them and match them, like the ones that have 8.7, those two are coupled to one another. Those are splitting each other. And then the ones that are 6.9, they're splitting each other. But since the J values are different, you know that the signals over here is not splitting with one of the signals over there because the J values are different. That's extra information. You don't need that to solve any of the problems in the problem set, but just don't be confused by it. It's kind of an extra information that can be helpful sometimes. This is a pretty big molecule. It's got multiple functional groups. There's a lot going on in it, so this one's kind of tricky. Let's move on to the next one. The next one has an interesting note here. It says disappears after D2O shake. So, and it's pointing to this little blip there, and it's trying to explain that there's a peak here that when you mix it with D2O, it disappears. And so I'm going to talk about why this happens in a little narrative when we're done with this. But for right now, what this is saying is it's a hint that it means that when this happens, it means this peak must be NH or OH, because those are the kinds of protons that exhibit this sort of behavior. And like I said, I'll explain that later, but it's a hint. It's saying that this signal right here, this little peak right here, that one is an OH or an NH. And that's helpful because you know the formula. You know the formula is C7H16O. So since there's an O in it, you can say, well, this must be an alcohol OH, because we know it's got to have either an alcohol or an amine, an NH, and we have no nitrogen, so it's got to have an OH. So we've got, right now, based on this note here, we can say for sure that the molecule's got an OH group in it, hydroxyl group. Okay, and then we can go through and figure out what else is in this molecule. And we're given some integration information above the peaks. So there's a 7473, there's a 1275, and there's an 11,238. These are integral values. They're just really big integral values. So what we'll want to do with those is take a look at, try to normalize the ratio to make it a whole number ratio, or as close as we can get to a whole number ratio. So the usual thing that you do is you take the smallest number, which is the 12,075, and divide all the other numbers by it. So I'm going to my calculator and I'm entering 7,473, and I'm going to divide it by the smallest number, 1,275, and I get a value 5.86. And of course, when you divide 12,075 by 12,075, you get 1. Then I'm going to divide 11,238, the area of the far right signal. I'm going to divide that by 1,275. That's going to give me 8.81. So that's trying to tell me the ratio of the areas of these peaks. It is the ratio of the areas of these peaks, but it's trying to tell me how many protons of each type I have. And this might look a little frustrating because, one, I can get, this isn't a whole number, it's some fraction of a whole number, and that's not a whole number either. That'd be hard, except that we know how many hydrogens there's supposed to be. There's 16. So we'll just pick the version that's closest to this ratio that gives us 16 overall protons. If you go with 1 of this type, 6 of that type, and 9 of that type, that gives you, when you add up 9 plus 1 plus 6, you get the 16 that the molecule has to have. So that's got to be the ratio. So that's helpful. We know we have 6H in the leftmost signal. We've got 1H in that middle signal that disappears, that's due to OH. We have 9H of this other type. And we also have TMS, tetramethylsilane, the internal standard. All right, well, let's see if we can figure out what kind of splitting pattern we're seeing here. We're getting something that looks hopefully familiar. There's a quartet triplet in a 2-to-3 ratio. It's a 6-to-9 ratio, but that, but it reduces to 2-to-3. So this is saying ethyl. So the molecule has ethyl in it, CH2CH3, and it has OH in it. But how do we get a molecule that's got 7 carbons and 16 hydrogens out of just ethyl and OH, do you think? Multiple ethyl groups that are identical. That is the way that you have to think about it. We're not allowed to have any other unique proton type, so we got to have multiple ethyl groups. In order to get a 6-to-9 ratio, 3 ethyl groups would be the way to go. So let's do that. I'm just going to write the 3 ethyl groups out here. CH2, CH3, CH2, CH3, and then the last ethyl group, CH2, CH3. That would account for all of the peaks and all of the area that we see in the proton NMR spectrum. So that's good. But we should also take a look at the formula and make sure we're not missing something. So let's go back and take a look at that formula. We've got C7H16O. We add up all the atoms and all the fragments that we've got so far. We've got 1, 2, 3, 4, 5, 6 carbons. So we're missing 1 carbon. We've got 5 hydrogens there, 5 hydrogens there, and 5 hydrogens there. That's 15 plus 1 here is 16. So we have all of the hydrogens, and there's 1 oxygen here. So we've counted for the oxygen. So the thing we're missing is a carbon. And that carbon can't have any protons on it, so it's got to be a carbon like this, where it's just carbon with no H's attached. And when you put that down, now you've got all of the pieces to put the molecule together. We've got this OH that has to go on the molecule somewhere. We have, in addition to the OH, we've got 1, 2, 3 ethyls. And then we've got this carbon that is going to link it all together. So the only way you can make a molecule out of this is to use that central carbon as the connecting point and put everything attached to it. So C with an OH and 3 identical ethyl groups. They're all the same through a combination of rotational symmetry and internal mirror planes of symmetry, which is why they give the same signal. So if we were going to assign these peaks, I would give the A label to the quartet, the B label to the small singlet representing the OH, and a C label to the triplet. And then over here in the structure, I would say the A signal belongs to all the CH2s. They're all identical, so they all get the same label. The B signal is the OH, and then the C signal is the CH3s of the ethyls, and that's that molecule. The tricks with this one are understanding the hint that the D2O shake causes one of the signals to disappear, and then identifying that there's ethyl, but there's got to be more than one ethyl by symmetry, because that's all you need, the 3 pieces to make a complete molecule. So molecules with symmetry have many signals that represent sometimes groups of the same type, multiple groups of the same type. All right, let's go take a look at another one. This one's got multiple spectra in it, and what it's saying here is an unknown molecule gave an NMR, IR, and NMR spectrum shown below. NMR, IR, and NMR spectra shown below. We've got an IR spectrum right here, and I know that because I'm looking at the x-axis, and it goes from about 500 to about 4,000. The peaks are pointing down. That it just looks like an IR spectrum. Hopefully you've looked at enough IR spectra that you can just look at that and go, yeah, I know that's an IR spectrum. We've got a carbon NMR spectrum here, which we're going to talk about in a little bit. We haven't specifically talked about carbon NMR yet in lecture, but we're going to mention it in a little bit. We did talk about it in the lab, but I realize not everybody's in the lab this semester. So we're going to talk about C13 NMR in a little bit. I'm just going to label these. I'll call this IR, label that IR spectrum. This is C13 NMR. It looks specifically at the carbon atoms. And then the big spectrum that I have here is the proton NMR spectrum, 1H NMR. And let's see what we can get for information out of the IR and the proton NMR, which we're really familiar with now. I'll blow up the IR spectrum and let's talk about it. 3350, broad, smooth, strong signal absorption. Does that strike anybody as like familiar, something you've seen before? Who wants to give a shout out to a functional group? Alcohol, yay, all right, awesome. Yep, this is an OH group of an alcohol specifically. And I think what I'll do is I'll put the label down here by the frequency, OH, HO. Specifically an alcohol, not a carboxylic acid OH, because they look very different and they show up in a different spot. Then one of the things that we've been working on when we see an IR spectrum is we tend to suggest you draw a line up from 3000 up to the top, and you look to see what's on the left side of it, just to the left and just to the right if there is anything. And in this case, we've got signal right here on the right side. That's characteristic of sp3 hybridized carbon to H bonds. What else? We want to get the stuff, the signals, the peaks that are in the functional group region from 1500 to 4000. And one of the things you might have a question about is, what about this guy right here? It appears, if you look really closely, I think it appears a bit below 1500. So I would say that's not one you need to worry about. If you thought maybe that was telling you aromatic ring, I would say, okay, well, it's good to consider that option. But two things I would say would suggest it's probably not an aromatic ring. First of all, there's no 1600 peak, which oftentimes is associated with the 1500. But more importantly, there's nothing over here in the space just to the left of the 3000 line, which is sp2 hybridized CHs. So I'll put a note here saying no sp2 hybridized CH. So if it did have an aromatic ring, it wouldn't have any CHs attached, and that's really pretty rare. So I would say there's what this molecule has is an OH and alkyl group or groups, but no aromatic ring. And there's a whole lot of other things that aren't there too. There's no carbonyl peak right here at 17 in the 1700 region. There's plenty of things that aren't there. The big things that are there are the OH and the alkyl pieces. So that's about all we can get out of the IR spectrum. But the OH is a really big hint. That's a super important part of this. And we know that we've got a molecule that has C5H12O. Let's figure out degrees of unsaturation on this one. We haven't done that yet, but maybe we should. I think this is an easy thing to do. So let's do it. Remember, degrees of unsaturation equation is 2 times the number of carbons minus the number of hydrogens minus the number of halogens if you have any, plus the number of nitrogens, all that plus 2. Take the whole thing, divide it by 2, and you get degrees of unsaturation. So we've got 2 times the number of carbons. 2 times 5 is going to give us 10, minus the number of hydrogens, and there are 12. And then we don't have any halogens. We don't have any nitrogens. We just have to add 2 to it, and we take the whole thing and divide it by 2. So we get the numerator in this molecule or in this equation is 0, and we take 0 divided by 2, and we still get 0. So there's no degrees of unsaturation. That means there's no ring, and there's no multiple bond of any kind. This is a totally saturated molecule, which is helpful because you know what not to look for now and what not to put in there. So when you start looking at chemical shifts, you don't have to worry about, oh, is that peak that I'm looking at associated with a double bond? Well, it can't be. So it narrows down your prospects a bit. So let's go take a look over here and see what we see in the proton NMR spectrum. I'll start by labeling the signals. I usually like to do that with lowercase a, lowercase b, c, and d. And what we're looking at here, make sure you're comfortable with where the axis is positioned. So the x-axis here is going from, on the high end, probably about 2 parts per million, down to a low end of about 0.8. So it's not the entire spectrum. It's just a portion of it that's been blown up so that you can see the multiplets really clearly. And this is all on the pretty far right side of the spectrum. Let's see what we should be looking for here. We know we have an OH group. We got that from the IR spectrum, and we know from the formula that we have an oxygen. So we can identify our alcohol OH as being associated with this signal right there, the A signal, because it's a singlet. And OHs don't split their neighbors. They're not split by their neighbors. One OH group has an integration of 1. There's only one small singlet in this molecule, and it's that. Then we've got a couple other pieces that we can get. Check this out. We have a quartet triplet pattern in a 2:3 ratio. That is a pattern that you've seen before more than once. What the peak is trying to tell you is the B signal is it's 2 H's that have 3 neighbors. So the quartet, in case this is new, let's decode this. There are 3 neighbors associated with that signal. So it's 2 protons that has 3 neighbors. So it's a CH2 probably next to a CH3. The signal over on the far right, the D signal, it's a triplet, so that means it has 2 neighbors. That is a CH3 because it's represented by a 3H signal. It has area that is telling us it's got 3 protons, but it has 2 neighbors. So that's a CH3 group that's next to a CH2. So this is trying to tell us ethyl group. So we have an ethyl pattern in this molecule. We have a CH2 next to a CH3. The CH3 is giving rise to the triplet on the far right, signal D, and the CH2 is giving rise to the quartet, which is signal B. Then there's only one other thing in the molecule we have to figure out, one other signal we have to figure out, and that's the signal at 1.3, this big singlet for 6 H's. When I see 6H, what I usually think is a couple of identical methyl groups. That's a really common way to get 6 identical protons. It's not the only way. You could have 3 identical CH2s. That's another way you could get 6 identical protons. But 2 identical methyl groups is a really common option. So I'm going to go and put that down as a possibility for fragments here. So a CH3 that doesn't have any neighbors and an identical CH3 that doesn't have any neighbors. Because it's a singlet, there are no neighbor protons nearby. So these protons that are represented by that big singlet can't be next to any other carbon with H's on it. So we have to keep them isolated. All right, we've got some pieces. Let's do some math to figure out, since we know the formula, if we're missing anything. We know our formula has got this C5H12O set of atoms in it. And let's see what atoms we've come up with so far based on our proton NMR spectrum. Let's count carbons first. In the ethyl group, we've got 1, 2 carbons. And then in the 2 identical methyl groups, we've got 3, 4 carbons. So what we've accounted for so far is C4. And for hydrogens, if we count the hydrogens, we've got in the ethyl group, there's 2, and then 3 more is 5. And then 3 more in the 1 methyl group is 8. And then 3 more is 11. And then 1 more, 12 from the OH. That's H12. And then we've accounted for the O by identifying the OH. So these pieces represent most of the molecule, but when you take a look at it, the molecule actually has 5 carbons in it. So we're missing a carbon. It's like one of the previous examples that we saw where there's a carbon that doesn't have any H's attached to it. So it's not really obvious that it's there from the proton NMR spectrum, but it has to be there because we need to get 5 carbons and we need this other carbon to link everything together. So that must be the missing piece. And that would get us up to, if we had that, if we put that piece down, now all of a sudden we've got C5H12O. So we've accounted for everything. And once you've done that, then you can put it together. So you just have to assemble the pieces. And sometimes you have to be careful about the way you put the pieces together to make sure that everything comes out right chemical shifts, right splitting, all of that. In this case, there's only one way to do it. There aren't 2 unique ways to put this molecule together. So that central carbon atom attached to 4 different things is attached to an OH, 2 identical methyl groups, and then an ethyl group, CH2, CH3. This works because the methyl groups are isolated from other protons. They'd show up as a singlet. We've got all the groups attached, and now we can assign the peaks with A, B, C, D. The A signal is the alcohol, OH. The quartet signal B is the CH2 of the ethyl group. The big singlet C are the 2 identical methyl groups that aren't being split by anything. And then the D signal is the methyl group that appears, the CH3 that appears in the ethyl group. All right, now that we've got carbon NMR data, let's talk about the carbon. So we can get the carbon NMR spectrum figured out. And if you knew a lot of carbon NMR, you could start with a carbon NMR, or you could look at the proton spectrum for a little while, and you could look at the carbon spectrum for a while. When we talk about carbon, this will become a little easier. But I'm going to label these carbon signals with capital letters A, B, C, D. That's telling us we have 4 unique kinds of carbons, but we know there's 5 in the molecule. So that means there's got to be 2 that are identical, because the molecule has 5, but we've only got 4 unique types. The molecule was this one. And the chemical shifts of carbon NMR work in an analogous way to the way that chemical shifts work in proton NMR, in that they're sensitive to chemical environment. So carbons that are de-shielded a lot because they're, say, next to an oxygen, they appear further down to the left. Double bonds, carbons appear in this region. Aromatic ring carbons appear in this region. Carbonyl, C double bond O, appear in this region. And then up here are sp3 hybridized carbons of alkyl groups, for example. And there's a table that I'm going to share with you that has all this information. But based on that, A being the most de-shielded, That's the one that's attached to the oxygen directly. Then we've got 3 carbons here, here, and here that are equidistant from the oxygen. They are 1 carbon removed from the oxygen. The CH2 is going to be the one that's the next most deshielded because CH2s are inherently a little more electron poor than CH3 carbons, just like how it works with proton NMR. So this is going to be the B signal, and then the C signal is representing the 2 identical methyl groups. You can also get probably a hint about this because the C signal is really big compared to the others. That suggests that maybe it's representing more than 1 carbon, but what we're going to talk about when we talk about carbon NMR is that it's not completely reliable. You can't count on that to help you decide how many carbons each signal represents. It's more complicated than it is with proton NMR. And then finally, the last carbon here, D, is the methyl group of the ethyl. The CH3, the ethyl, it's the furthest away from the oxygen. It is the most shielded of all the carbons, and it shows up on the far right side. So that's the full interpretation of this molecule. And I'll post a copy of this solution set on Canvas. I have a copy of a solution set to these problems that I worked out last semester, but I'll put this exact one up so you can refer to it later. But these are the things to look for, not necessarily in the exact order that I looked at them, but you got to make sure you get all the information out of all the peaks so that you can get all the right fragments and then put them together right. Yeah, what you'll see when you look at my old exams, I give the integration values. When we did an exercise in the lab, you just got integral traces and you had to get a ruler out and you had to measure them, and then you had to figure out what that whole number ratio was. So you'll see 1 or 2 scenarios on an exam. I'll either give you straight up the number of hydrogens it represents if I'm like trying to make it as easy as possible. I'll say 1H, 2H, 3H, 4H. If I don't do that, I'll at least give you a number that's the ratio. It might not be a whole number ratio, but it might be 1 to 1.5 to 1, and then you'd have to figure out, oh, that's a 2 to 3 to 2 ratio, for example. But it's going to be real simple math. It's not going to be really hard things that you're going to need to do a lot of calculation on, because the thing is that it takes a lot of time to do, and that's not what I want to spend our exam time doing. I want to spend our exam time like demonstrating interpretation skills rather than manipulating ratios. So that's my philosophy anyway. And as far as like exams go, multi-step or multi-spectra interpretation questions take a long time. They're challenging, and so the whole exam cannot be like this. There might be 1 like this on the exam. Most of the old exams you look at, there's 1 like this, or maybe 2 easier ones, or 1 more involved one. And then the rest of it is smaller questions. And when you get a question like this, it isn't like you have to get the whole molecule to get any points. If you get parts of the structure, you'll get partial credit. So that's why I encourage you to take this fragment approach. When you see an OH in an IR spectrum, if you write that down, that illustrates that you found that piece, and it says to me, okay, you understood that part, so that's worth some partial credit. Saying sp3 hybridized CHs, that tells me, okay, you recognize that, that's worth some partial credit. In the proton NMR spectrum, if you can pick out an OH group and where it is, that's more indication that you know what's going on. If you identify key fragments like ethyl, that's really big. Or a couple of identical methyl groups, that's also really big. So if you get all the pieces but just can't quite put it together, that's fine. You'll still get like pretty good credit for the molecule. And I'm pretty generous with partial credit on these. My experience is a lot of times with these multi-spectra ones, like half the class gets the whole thing, and then the other half of the class typically gets a lot of it, many chunks, but doesn't quite get it. But they all get really pretty good credit on it. The only thing would be is if you don't do it, you can't get any credit. So just try to figure out what you can about it, and don't leave it blank. As long as we're talking about it, it's a good idea to go to Canvas and get the old exam ones from this course that I've taught, that I posted. Those are the ones from fall 2024 and fall 2023. You can see the kinds of questions I asked, the difficulty level. Try them out, see if you can get the right answers. The keys are also posted, so see what you can do, and just gives you a sense of how well you're understanding the stuff. So those are some interpretation problems. Now what I'm going to do is tell you a little bit more. We're going to go back to more of a lecture and just talk about some last NMR details about things you can learn from NMR, carbon NMR, and then a little bit more about why that trick where the D2O is added and OH and NHs disappear. We're going to talk about that. I think we have enough time to talk about why this D2O exchange trick works. So here's the situation. If you have an alcohol which has an OH group on it, or an amine with an NH, one or more NHs, these protons rapidly exchange with other OHs or NHs or deuterium. So what people discovered is you can put D2O in with these molecules, and D is deuterium. That's heavy hydrogen. That's a hydrogen atom that has a neutron. Normal hydrogen, a proton is just a proton and no neutron, but deuterium is proton and neutron together. And it behaves chemically like a proton, but it's invisible in the proton NMR spectrum because it's not proton. So we don't see it. And so what happens when you mix these together, there's an exchange process that goes on, and it's reversible, but the H and one of the D's here exchange. So you get an ROD and then an OHD here. Similarly down here, when you put an amine in with D2O, these two exchange rapidly in a reversible fashion, and you get a deuterium in place of the hydrogen on your amine, and then another HOD. So you'll see a new peak for H. You might see a new peak for the HOD, but what'll happen is the OH or the NH will disappear because it becomes a deuterium, and deuterium doesn't show up in a proton NMR. So that's why this works. It's called a deuterium exchange experiment. And it's super easy. You just take your molecule, you do a proton NMR spectrum of the molecule without deuterium, you locate all the peaks, and then you look at all the little singlets that you might have, and you think, well, is that singlet an OH or an NH? Then you add a drop of D2O, you shake your tube, you put it in the NMR spectrometer, and you retake the spectrum, and you look for all the peaks that disappear. And any peaks that disappear, those are your OHs and your NHs. It's a pretty cool, really easy, simple trick to definitively say what peaks are OHs and NHs. And that's good for today. Next time we'll come back and we'll talk about carbon NMR in a kind of an abbreviated way. We've seen it in the lab before, but and then we'll move on to the next chapter, which deals with oxidation and reduction reactions.